Welcome back to the channel. In today's video, we're going to talk about multi-stage signal processing, how we can take data that looks like this, that's uninterpretable, that's really cluttered, and make it look like this by combining many of the techniques we've talked about in previous videos, like signal processing techniques like Standard Normal Variate, Z-scaling, square root scaling, and method chaining. So trying to get the best of both worlds so that we can take data that we collect on our own portable NIR device and make that something very useful by combining our expertise of analytical science and data science. Let's get started. So in this notebook, I have my over-the-counter pharmaceutical drugs, and I've analyzed them by near-infrared spectroscopy. In the first cell, I've got all the standard imports. However, let's get to the more interesting part as we begin cleaning this data up, and we can see that this is our actual spectral data. So I've got vitamin B, acetaminophen, fexofenadine, and my NIR spectroscopy data on the right side at these various wavelengths. So the idea is to now apply techniques to help us understand the type of data we have and leveraging multiple signal processors in the process. So we've got our apply SNV, which will help us to remove some of the scatter that comes from spectroscopy data. We've got Savitzky-Golay, which will help us smooth out this data. And then we have a few others you may not have heard of, such as detrending the data, so helping us to remove that slant that can appear in our baseline, as well as the multiplicative scatter correction technique. And so all these functions can be used as they take in a data frame and return a data frame. And so we can pipe these together, and it's really important to consider how we build these techniques for this particular purpose. So let me show you what this data looks like without any signal processors. It's all overlapped. It's all really scattered. We can see that the baseline is clearly sloped up. And so we need to do something in order to help us understand the type of data we've got, to say something about it through other modeling techniques. So this is why we do our signal processing. So the first and one of the most common techniques is the Standard Normal Variate. And so we have our data frame. We're using loc to select just the analytical data. I'm now using this pipe technique here and then transposing the data and plotting it. And when I do this, you see that the data comes together and it's much tighter. So if I remove this and run this again, you can see how we go from a spread out set of spectra to a more tightly packed. And this is, of course, because you're removing a lot of that scatter. Now, if I apply my Savitzky-Golay with a window size of 3 and a polynomial order of 1, we will also see an improvement in that the data becomes even tighter and a little bit more smooth. So you can see we're having a very visible impact on this data. And lastly, let us detrend the data and using the constant, which just subtracts the mean of each spectrum. And you can see that we have a very different look. So now the data that was going up and to the right is now a little bit more flat. And of course, we don't have to use all of these. We can even change the order or reduce them. And it has a very substantial impact on the data that we've got. I can group by the sample, and that gives us a simplified view of the data for our own consumption. And I will eventually have this data in GitHub, but we can see the impact of our various preprocessors on our various drug classes. And it gives us hope that we might be able to do something like PCA or TSNE to visualize this in a different manner. So let's do that. So that was the spectra view. Let's look at the multivariate view. And I've got two functions called plot PCA figures and plot TSNE figures. And this just helps us to more quickly see the impact of our preprocessors. And so let's run this really quickly, in which we are going to separate our X data or the analytical data from our Y data, which are the samples. And then we'll go to our preprocessed data. And what I just want to show you here is just how this will essentially produce the same output as before. This is the data we saw above with just our apply SNV. And so it's a very similar output. And so now if we continue to scroll down, I've got 4 different pre-processing chains, X1, X2, X3, and X4. X1, this is basically the raw data going in, Z scaling, and then being plotted by either PCA or TSNE. Then I steadily chain more methods using this pipe here, and we can continue to do this until we are satisfied with the signal. But the challenge with looking at just the spectral data is that it's really hard to understand, is it making a meaningful impact? And this is where decomposition techniques like PCA and TSNE really come in handy. So let's take a look at that. And first we'll do PCA, one of my favorite techniques. And this will compute the scores and produce the scatter plots, as well as apply our coloring by the sample type. And so if we look at this first figure where there's minimal preprocessing and it looks very messy, it looks like almost a hopeless situation. And pretty quickly, as we apply SNV, Savitzky-Golay, and even more in preprocess 4, we see that we're having a lot of different impacts on this data, and primarily tightening many of these clusters by removing that scatter and building some distance between the groups, helping us to gain confidence that we can build models to help us understand this data. We can also see the impact of changing some of these parameters, like changing our window size to 5, and how we can really alter the shape of this data here. And so a lot of work to determine what are the optimal conditions, and this could be done using other techniques like grid search and many more. And so let's also look at the impact if we look at our manifold technique, and we have a very different set here. So it's nice because we can see how they kind of latch on and pull things away a little bit differently. So the loratadine here in light blue is a very tight cluster. It's a little bit more spread out here. The darker blue, the vitamin B complex, is also tight but more centralized in this plot here. But the part that's really cool, if I go back to the 3.1 or 3.2, it's really cool because we can begin to see some things that are quite insightful with this data. For instance, we have this green cluster of points here, which is between the red acetaminophen and the purple ibuprofen. And this green is the Advil Duo pill, which has two APIs, ibuprofen and acetaminophen. It is nice that we see that clustered in the middle. Interesting as well as we see our allergy medicines, loratadine and fexofenadine, also separated and pushed further to the right than the other drug compounds. And then our vitamin B clustered, interestingly, close to ibuprofen. And probably if we were to look at a third dimension, we would see that really popping out in component 3. And in TSNE, we see them separate even more. And so this gives us hope that we can take what we know about how to make high quality measurements and what we know about signal processing and build fantastic models, help drive new insights through visualizations like this, and even help us to understand the chemicals around our home. So in one of the upcoming videos, I will actually do that, build a data set based on the over-the-counter pharmaceuticals, the plastics, the food, all the things we have, cosmetics around our home, and apply many of these same techniques so we can begin understanding how do these compounds interact with each other in this multidimensional space when collected on a device like this that allows us to generate these types of spectra. If you want to be notified when it comes up, subscribe to the channel. I'll see you in the next one. Peace.